I'm Frederick Ziola. This is my speech to inform. Computer graphics have gotten incredibly realistic. There's no more denying it. You can play a game on your laptop that's indistinguishable from reality. But what you might not appreciate is the insane amount of university level maths and incredibly clever engineering that goes into making you feel like you're really standing in Night City. Just a decade or two ago, games looked flat, static, and blurry. Now you can see light from a single tiny detail illuminate fog, bounce off a puddle, and brighten the whole world around it. Today, ray tracing is the driving force behind this remarkable realism. Ray tracing can accurately simulate light, and with some clever optimization, it's even feasible for real time applications like video games. But first, let's address the checkbox fallacy. That's what I call it, at least. Corporations like Nvidia understand that the public doesn't really know what ray tracing is, but it sure does sound high tech. Ray tracing is an incredibly general term that can describe a number of techniques. For example, you have Raymarch volumetrics, which we've been using since Crysis all the way back in 2007. Just ray trace shadows. Sure, they look better, but they're still just there so you can have that RTX on high. Call of Duty Modern Warfare from 2019 supports this feature, but you'd never notice the difference in fast-paced gaming, and it hurts your frame times by 20%. And the real kicker, full path tracing. It looks amazing, but it's rare to see and it's incredibly slow. Games like Cyberpunk 2077, with ray tracing overdrive enabled, or Portal RTX use this technique, and they require nothing short of a $1,000 gaming rig to run even at playable speeds. Now, ray tracing isn't always better. Believe it or not, ray tracing isn't a one-size-fits-all solution to game realism. Comparing a modern game using traditional techniques to a ray-traced one, you'll see they look close to identical. In fact, in games with a more artistic direction, ray tracing can take away from the artist's intent. And it's slow. Ray tracing techniques can be 10 to 1,000 times slower than traditional renderers. However, Nvidia has invested tens or even hundreds of billions of dollars into developing ray tracing technology. Once people realize that traditional techniques can look just as good while being 10 times faster, all of that goes down the drain. So getting that supports ray tracing label on everything possible is their last-ditch effort to keep all that money from going to waste. Now, this isn't to say that ray tracing isn't an amazing technology, it's just important to acknowledge that it's more than just a yes or no. After all, a Civic and a space shuttle both get you from A to B. We have different names for them, but ray tracing seems to be the single blanket term for all remotely related tech. So with that out of the way, how does ray tracing actually work? You may have heard that it calculates the path of light rays, but what does this really mean? Here I'm going to explain the basic technique behind path tracing, which is the most realistic form of ray tracing today, and it follows every single photon flying through the scene. Now it all starts with the camera, literally. Every pixel on the screen shoots a virtual ray of light into the game world, which we'll call the scene. Ray intersection is the heart and soul of all ray tracing. Using some awesome math that we don't have time to talk about, the one single point where a ray intersects the scene is calculated. Now where a ray intersects, it bounces. Each ray keeps track of how much light it collects and how much is absorbed along the full path it follows. Every time it hits a surface, it's scattered in a random direction and some of its energy is absorbed. Imagine a laser beam hitting a glass of water. The beam will reflect off the outside of the glass, bend, or refract into the water, and each new path can perform the same interactions thousands of times. Once a ray hits a light source, or it flies off into space, we compute how much light was transported back to the camera, and that's used as the color for a single pixel. Now there's more to it than this, of course, but this should help you understand the basic idea. We have some simpler techniques as well, like ray trace shadows that I mentioned earlier, which cast a single ray directly towards a light source to determine whether or not a point is lit. These techniques can improve visual fidelity, but they often don't add much, especially for the untrained eye. Now, you might be thinking, it sounds slow, right? Well, yeah, it is. Calculating just a single path of light is fairly simple, but in reality there are tens of trillions of photons flying around at any given instant. Now, we don't need that many to get a nice image, but simulating even 1,000 paths of light at once is remarkably difficult. Now, this is where optimization comes in, and with it, much of the clever engineering I mentioned earlier. Before, when I said light scatters in a random direction, that's exactly where most of the optimization happens. Techniques like multiple importance sampling, restir GI, and metropolis light transport all pick these scatter directions rather intelligently. The goal of these techniques is to send more rays in directions that will gather more information for our image. For example, restir GI allows path resampling, or in layman's terms, once a single good path is found, we can reuse it with some small variations instead of starting from scratch every single time. Using a combination of statistics, linear algebra, and multivariable calculus, we can make our renderers up to 100 times more efficient than before. Now, even with this massive speedup, it's just barely fast enough for video games. Today, we have learned about ray tracing, what it really is, how it works, and how it's almost here for video games. Hardware is only getting faster, and our code is only getting smarter, so in a few years, who knows? We could have mathematically perfect lighting in games. If you're interested in computer graphics, there's no better time to start than right now. It's the perfect combination of math, art, and software engineering, and it only gets cooler with time. I hope this has inspired you to learn even more about ray tracing and computer graphics. It's always fun to understand how your favorite games do what they do. Thank you.